Okay, so our goal is to find the mass of the cylinder, and we want to find the moment of inertia with respect to the z-axis. Okay, and what makes this problem particularly hard, we can't just go in our book and use our nice little formulas because look at our density, right? So we have a formula for density that involves our radius. So yeah, the density at this point is not going to be the same density at this point, so it makes things a little bit complicated. Well, there is a formula / a relationship that we can use to cut all that shit out. So dm is equal to rho dv. So differential part of mass is equal to the density times some differential amount of volume. So I'll leave it rho. And then dv is pi r squared times h. But this is all differential, so is it really just r, or is it some change in r, right? And then what is rho? Well, we said rho is this thing here, so it's k plus a r squared. And again, there's going to be some change in r. So the way we can describe all this stuff is we're going to say, okay, so we have a cylinder, right? We have a cylinder here, and there's some differential mass, right? Well, how can we describe this differential mass? We can describe it with a differential amount of density and differential amount of volume. Specifically, we can take little disk. So if we take this little disk here, and we go like that, you can describe this little differential amount out of disk, and then times it by some height, and then we have everything. That's everything you need. Okay, so I'm going to go back a step, and I'm going to erase this stuff, because it isn't that useful until you know how to use it. So I want you to start off by defining what type of method we're going to use. So we're going to use the method of disk. Okay. So you're like, what is the method of disk? Well, it's the idea that we're going to have these disk, a circle with some thickness to it, and that's going to be the way we describe this. So what's the disk? A disk is, in this case, it's going to be the area times some height. Okay, and since it's a differential amount, it's going to be some dA times h. So specifically, dA is the differential amount of area. The differential amount of area for a circle, so dA is what? It's going to be pi r squared. Let me erase that. It's going to be the derivative with respect to r of pi r squared, which is 2r pi dr. Okay? So that's the idea. So we say that this is here, 2r pi dr. And, you know, you pay all this money to go to university, but they can't provide you some fucking extra pins? What is that about? Okay? So often in life, you need to buy your own expo pens. Okay? Okay, so area times our height. So we have our dV is what? It's going to be 2r pi h dr. And real quick, I have my guy right here. You guys can see this. Look, this is it. This is our disk. It's our disk formula. Okay, so that's dV, and then times that by what? Rho. Okay, so our disk is going to be 2r pi h dr times k plus ar squared. And then what is that? Well, it's going to be, okay, full transparency. I did it, and then I forgot this little a. So when you're learn how to distribute properly, make sure you learn how to distribute properly. It's very important. Okay, with this, I just want to group this a little bit nicer. So I'm going to keep the constants out in the front. So I start by distributing it. So it's going to be 2r pi h k dr plus 2 pi r h dr times this. So 2 pi r h dr times a r squared. Now I'm going to factor out the constants. What are the constants here? So pi, h, k, and 2. And then in this case, it's a, h, r, not r, pi, and 2. So I'm going to factor out as many constants as I can. So 2 pi h. Okay, there's only a k on this side. There's no k on this side. There's a on this side, so it'll be like this. K r plus a r cubed, right? R cubed here, and then dr. So this is our integrand. So if we want mass, we take the antiderivative of both sides of this relationship. Right? We do this, we integrate both sides, that's how calculus works. And then we can say that mass is going to be equal to what? It's going to be, oh, let me write this a little bit nicer, 2 pi h integral, then here's our integrand, kr plus ar cubed dr. And what's our bounds? Okay, our bounds is just big R, right? Big R to 0. Okay, so now when we integrate, we get 2 pi h. Okay, r is what we're integrating with respect to, so it's going to be k over 2 big R squared. I'm going to instantly put the r, big R into little r. A over 4 r to the 4. Sorry, I said that kind of wrong. And then this little r turns into big R. I'm just inserting the bounds in. Okay, so this is your mass. Yeah, kind of a weird mass, right? You usually would think of your mass as some simple number in kilograms. Well, in this case, we aren't using little kilograms units because we're fucking physicists here, right? So we're only going to go in variables. Okay, what do you want now? Like, you want so much out of me. You want IZ? Okay, I can give you IZ, okay? So to r squared dm, right? Don't believe me? If you don't believe me, you can go fuck yourself first, but zoom in on that bitch, Andrew.
Yeah.
Okay. I like glitter. Okay, so we want to find moment of inertia. dm, let's frickin' put dm in here, right? Like I like dm your side chick. So we're gonna put dm into here. So, oh god, 2 pi h, then we'll have r squared, and then this part here, kr plus ar cubed, dr, and we're integrating from r to 0. Okay, so what can we do now? Okay, so r squared comes in here too, so it's 2 pi h, integral big R to 0, k r to the 4th plus a r to the 5th, dr. Okay, now we can integrate. It's going to be 2 pi h, k. Ooh, look at that, guys. Fucking almost caught me right there. Almost caught me fucking slip. Right? R squared, r cubed. R cubed. There. Okay. Don't want to fuck up on that. You know, you don't want to lose all your points for no reason. Plus AR6. 6. And we're integrating from big R to 0. Right, so what does that mean? That means you can erase this guy, and then you can make this into a big R. You can make that into a big R. So there you go, there's your answer. And if you want, okay, so you want to find the radius of gyration for this paraboloid. And you know that the radius, its max radius is 2. I'm sure all of you guys know what 2 inches looks like. And then I'm sure, I don't think most of you guys don't know what 8 inches look like, only I do. But we want to know the radius of gyration. What's the formula for the radius of gyration? Okay, well we know kz is equal to the square root of what? Iz over m, right? Okay, so you need Iz and you need m. Kind of a lot of information, right? Well, what is Iz? Okay, you don't really know what Iz is, right? You can't just use some special formula. So we have to use d Iz is equal to r squared dm. And then it's like, oh fuck, what's fucking dm? dm is what I do to your girlfriend, okay? Rho dv. Okay, so we have differential amount of mass times the differential amount of volume. Why don't we define what our volume is? Okay, so first our volume. A volume for the disk. A disk that looks like this, right? And then dot, 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 right? It's like a circular disk. So it has some thickness, right? So here, yeah, we could call that thickness dx. We don't know what that thickness is. We only know that it's some differential amount of thickness, so we call it dx. Okay. So we have, well, before I do that, why don't we just call our thickness, so x equals thickness. Then we say dx is equal to the derivative of thickness. We'll leave it like that, okay? And then what is this? This is a circle, so it's pi r squared x, where this is the height and this is the radius. Well, what's our radius? Radius, okay, so it starts, our radius goes from 0 to 2. So we know r is equal to 0 to 2. Okay. Is the radius y or is the radius x? Well, okay, so it's getting bigger as it goes from here, 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 here. So it looks like the radius is x. So we say r is equal to y. And if you don't believe me, check this real quick. So x max is 8, right? X max is equal to 8. What is r max, or what is y max? Well, it's 8 equals y max. And how do we know this? Well, look at it. It says y cubed equals x. So 2 cubed is equal to 8. Oh, by the way, yeah, 2. Okay, so this is the relationship that tells us all this. And that's important because our volume is not fixed. We have a differential amount of volume, right? So to describe this disk. So we say dV, okay, let's just start with V. We say V is equal to pi y squared x. Y cubed equals x. Y is a function of x. We want y, let's get y by itself here. So y is equal to x to the 1/3. We got y squared. So y squared is equal to x to the 2/3. So this volume is pi x to the 2/3. And then hold up. Okay, actually, let me just write this x in the parentheses. The x by itself earlier, right? I said we have a differential amount of thickness. So I'm going to call this dV. I'm going to call this dV. I'm going to call this dx. Okay, now if that was confusing, I'm going to explain the logic again. We have a disk. We have a disk and this paraboloid. We can describe this paraboloid with the disk. The only way we can do that is by using a differential amount of thickness. And then we can relate the radius to the variable y, but then our variable y is a function of x. So yes, there's a lot of fuckery going on. And I can see why you're confused, because I am too, but we're in it together. Okay, well this is dV. So now you know that dV, well you know that dm is equal to rho pi x to the 2/3 dx. Okay, good. And you want mass by itself, so you integrate mass. P pi and x to the 2/3 dx. What does x go from? X goes from 0 to 8. Right? 0 to 8. Okay. So now we can integrate. So we know m is equal to rho pi, and x to the 2/3, when you integrate it, it's going to be x to the 2/3 plus 1. So it's going to be x to the 5/3. 5/3. Pause real quick. Okay, sorry about that. Your girlfriend was calling me, so I had to check my phone real quick. It's not because I had to check my answers. Yeah, x to the 5/3, 5 divided by 3, that's our integration. And it goes from 8 to 0. And then we know that this is rho pi 3/5 and 8 to the 5/3. Okay, so this is some number, and we're just going to leave it and stay tuned. Okay, admittedly, don't use this formula for this one. The formula we want to use is I is equal to 1/2 mr squared. Okay. Pretty low energy dynamics defeated me. Yeah, so I made the number magically appear. Okay, all right, I don't want to show you guys me typing my calculator. Nonetheless, let's take this guy. Okay, oh my god, what the fuck, dude, we gotta do differential. It's differential again, so it's di dm r squared. Yes, life is fucking miserable sometimes, I know. Okay, so what do? Okay, you say I is equal to the integral 1/2 dm r squared. R squared is what? R squared, r is equal to y, so it's going to be y squared. Y squared is equal to x 2/3. And then dm is what? Okay, this is dv, this is dm, so it's going to be rho pi x 2/3 dx. And what is this integrating from? 8 to 0. Okay, so we know it's going to be I is equal to, okay, we're going to pull out all the constants, pi and rho. So rho pi over 2, integrating from 8 to 0, x to the 4. X 2/3 times x 2/3 is x to the 4/3 dx. What is this? This is going to be, okay, integrating this will be x to the 7/3 divided by 7/3. So it's going to be rho pi over 2 times, I'll write it out for you guys, 7/3, 7/3, 8 to 0. And we'll write it out a little bit nicer, 3 rho pi over 14 x. Instead of x now, I'm going to insert the 8, 7/3. And Andrew, what's the number say? What is this number? By the way, you guys should be able to do this in your head. Like, is this expected? You guys should be able to.
It's going to be 86.17.
Rho 86.17. Okay, so this is your I, this is your mass, and that's your kz. So kz, as you guys can guess, the rows will cancel. The rows will cancel. So it's just going to be 86.17 divided by 60.32. And Andrew, what is that number?
It's going to be 1.195.
1.195 units inches. And this number looks awfully familiar to myself. I don't know why. Yeah, that's kz. Okay, so the problem goes, if a roller A moves to the right with a velocity VA, 3 meters per second, determine the angular velocity of the link and the velocity of roller B at the instant of theta equals 30 degrees. And this is the diagram. So B is the top roller, A is the bottom roller. And this guy's the one that's going to teach you how to do it all. Yeah, you're going.
It was been going?
No, it's going now.
Okay. All right, guys. So we're going to figure out what the problem is asking us here. And so we're going to determine the angular velocity with using our VA velocity and our VB. And so we know VA is going to be only in the x direction, and VB is going to be only in the y direction, the negative y direction. And so we're going to use the relationship, and it's going to be VB, these are the small one, VB equals VA crossed with, no it's not, it's going to be plus omega crossed with RBA. And our RB over A is going to be just the length right here, which is 1.5. But we got to put it in terms of since it's going to be a vector, we're going to put it in terms of our x and our y component. So let's just figure out what each one of these variables is going to be.
Okay, you're going.
All right, guys. So we're going to be figuring out what each one of these variables is going to be. And so VB is going to be only in the y direction. So what we could do is we could just do 0 VB. And then we could do VA, and it's going to be only in the x direction. So we'll have 3, 0. And then our angular velocity is going to be in the z direction. So there's no I components or j components. So it'll just be 0, 0, and then we'll have our angular velocity. And then our BA is going to be, that's just describing the vector from RA to RB. And so what we're going to be doing is finding our RBA in the I component, which is the x direction, and it'll be negative 1.5 cosine 30. And then we'll do the same thing for our j component, which is going to be positive since we're going up from RA. And so it'll be 1.5 sine 30.
Andrew, can you write a little bit harder because of the pen?
Yeah, okay.
And then also I want you to write a negative sign in front of your VB because it's only going down.
Oh, yeah. Yeah, we do have a negative right here. These are zeros.
Yeah.
All right. So then what we're going to have to do is we're going to plug these into our calculators to make it a little bit easier for us. So we'll have negative 1.3 for these values here. It'll be negative 1.3 and 0.75. All right. So then we're going to be calculating the cross product of our angular velocity and our RBA. So it'll be cross with RBA. So then we'll have our I, our J, and our K. Sorry, guys. And we'll have 0, 0, and then our angular velocity, and then we'll have negative 1.3, 0.75, and then 0 since there is no component for our RBA in the
Can you make it more, make the decimal a little bit bigger?
the decimal. Yeah. All right. So for our I component, it's going to be 0 for our first, minus 0.75 W, omega, I mean. And that'll be our I. And then for our J, this marker. For our J, it's going to be 0 minus, which turns into plus because we have negative 1.3 omega. And that'll be our J component. And then for our K component, it's just going to be 0 since we have zeros in our angular velocity vector. So then it'll just be plus 0K. Which then we'll simplify it. When we put it into a better notation, it'll be negative 0.75 omega for our I component, and then negative 1.3 omega for our J component. And then, if you wanted to, you could put 0 in for our K component. So that's just our cross product between our angular velocity and the RBA. So then we have to put this back into our initial equation, which was the VBA equals VA plus omega cross RBA. And so we'll come here. And so we got 0, negative VB will equal 3, 0, and then we'll put the 0 here for our J component, which actually we don't need to, since we have
No more K components.
no more. It's all done. All right. So now we're just going to be adding what we calculated down here, which is going to be 0.75 omega, and then negative point, or negative 1.3 omega, and then we'll add these. So then we'll just bring this down here, just not to get confused. It'll be 0, negative VB, and then it'll be 3 minus, for our component, it's going to be 3 minus 0.75 omega. And then for our J component, it's going to be just negative 1.3 omega. So then since we have no velocity of the B in the I component, we don't need to worry about that. Or actually, never mind, I lied. We do need to worry about that.
Two equations, two unknowns, right?
Yes, we do have two unknowns. We have VB and angular velocity. And we're going to be calculating for our angular velocity first by setting the I component of our VB and the I component of what we have over here equal to each other. So it'll be equal, 0 equals 3 minus 0.75 omega. It'll be negative 3 equals 0.75 omega. And if we could do this in our heads real quick, it's just going to be 4, negative 4.
One second, it looks like you forgot a negative.
I forgot to carry this negative over here. So then it's positive 4.
Which means it's in the
So it's going to be in the positive
direction, which is the
Z direction.
counterclockwise direction.
Yeah, exactly. Because if you use your right hand rule, you curl that way and you're pointing this way. So out of the board is where our angular velocity is going to be going. And if you want to put units on that, it's going to be 4 rad per second.
Correct.
All right, so now we're going to be calculating our VB, which is, we're just going to set these equal to each other, our J components together. So, down real quick. So we'll have negative VB equals negative 1.3 omega. And so we have omega here that we just calculated, so we're going to plug that in for here. So we'll have negative VB equals negative 1.3 times 4,
5.2.
which equals 5.2. And we'll just get rid of these negatives here. So it'll just be 5.2. And what was it?
Meters a
per
second.
second.
And we should note that it's 5.2 meters a second going downwards. So once you put an arrow next to it.
In the J. In the J
Okay.
component. So like that.
So we're going to zoom out for this whole problem. Okay. There you guys go. So this should make sense. We have a ladder on the wall, right? And it's going down because its front leg is being pulled out. So it's going to be rotating positively towards the ground. And it should be increasing in, well, its speed should be going down towards the ground at the top one. So those are your two answers. Start reading the question.
All right, guys, so we have this question here. It's the flywheel rotates with angular velocity of 4 theta to the 1/2 rads per second, where theta is in radians, and we're going to determine the time it takes to achieve an angular velocity of omega equals 150 rads per second, and we're given when t equals 0, theta equals 1 rad. So this is going to be our flywheel here, and our angular velocity is going to be going in the positive direction. And so what we're going to do here is we're going to note that omega equals d theta over dt. And so we have this relationship here. And so with our given equation for omega, where it's going to be a function of theta, so what we're going to do is we're going to put dt on this side, and we're going to put d theta over omega. And we're going to integrate it this way. So we'll have dt, and then it'll be d theta over omega. And so we're going to have to pick our boundaries here.
Can you make that look a little bit more like omega?
Oh, it faded away. Not bad.
Okay, that's good. Well, also, by the way, you need to go back to high school and learn how to write your integrals.
This is great.
Leave a comment if those are the fucking ugliest integrals. If like, if you're a 40-year-old math professor, that's your integrals. But come on, man, you're younger. You can draw some nicer integrals. There we go.
Oh, there we go. Oh.
I don't even know. That's fucking worse, man.
All right, there we go. There we go. So we're going to be using this given relationship, and it's going to be t equals 0. When t equals 0, theta equals 1. And so we're going to be starting. So it's going to be 0, and then t we're going to be solving for.
Forget about it. This guy dropped the cap 2 times.
And so when t equals 0, our theta is going to be 1, and then we're going to have our theta here. So then now we're going to plug in our given equation for omega, and then this is just going to be equal to t, and then we'll integrate from 1 to theta, and it will be 1 over 4 theta to 1/2 d theta. Just like that. And then we want to integrate for theta. And so to do this integral, we could just do t equals 1/4 outside the integral. And then we could bring the theta to the top, so then it would be negative 1/2 d theta. And don't forget the boundaries. Then this will equal 1/4.
Right to the right.
Huh?
Right to the right, please.
Up here?
Yeah.
All right. So we got t equals 1/4, and then it will be times theta to 1/2 times 2, just like that. And that would be from 0, or no, from 1 to theta. So then we'll do this. It'll be this minus square root 1. So then this is going to be our t, but we still have a variable theta. So what we're going to be using is our max angular velocity to solve for theta in this equation. So what we'll be doing is 150 equals 4 theta to the 1/2. 150 divided by 4 is equal to theta to the 1/2, which is just a square root. So then it'll just be 150 over 4 squared is going to be your theta. And
Okay, so 150 divided by 4. Let's think about that. That's the same thing as 75 divided by 2.
we got differential equation you got over here.
Okay. And then 75 divided by 2 squared. We'll let you figure that out for yourself in the comment section. Let's keep going.
All right. Should I just?
Yeah, just put it right in there.
All right. So then we have this right here. we're going to plug in our data here to this equation. It's going to be like that. And since our data here has a square root over it, we could get rid of this squared here, so then it'll just be 150 over 2 minus 2 square root 1. And square root 1 is just 1. So that's just 2.
1 second. Square root theta is equal to 150 divided by 4 squared. But there's a 2 in front, right?
Yeah. And then,
Wouldn't it be 2 times 150 divided by 4?
yeah, and then don't the 2's just cancel out? Or the 2,
Nope.
the 2 here.
Is this a class?
No.
No,
Oh, you guys are fine? Okay. We're still locking up.
Okay.
So when you guys leave, just make sure it goes on.
Appreciate
Okay.
it. All right, so we got this right here,
Pause.
18.25.
Okay. So, yep. And if you simplify this, right, it'd be 75 minus 2, which is 73 divided by 4. And if you put that in the calculator, what do we get?
And we got 18.25 seconds.
There we go.
And that's going to be the time it takes to achieve an angular velocity of 150 radians per second. So it's just going to be, keep spinning for 18.25 seconds until it reaches that max angular velocity.
All right, good.